welcome all of you. This is a tradition of the ICM since 1994. I have chaired the committee who selected the lecturer of this year, and the other members of the committee were Maria Esteban, Raman Parimala, Claudia Sagastizabal, and Anatoly Fershik. The committee had the pleasure to nominate Georgia Benkart from the University of Wisconsin as the 2014 ICM Emmy Noether lecturer. Before I say a few words on Georgia Benkart, so I will invite Ingrid Dobshi. There is something new in the presentation of the ICM Emmy Noether lecture. So Georgia and Ingrid, please come.
So, the Emmy Noether lecture, although it's not a prize award, is a high honor of the IMU, and it was the only one that didn't have a token, something to remember the event by. So we decided to have a special plaquette designed. It has on one side a portrait of Emmy Noether, and on the other it shows ascending rings, for which of course she is known, and we will present it, and I want to present it here to the Emmy Noether lecturer. And I don't know whether there's probably it's impossible for a camera to zoom into it, but it's an object of great beauty. It was designed by a very talented artist in bas-reliefs, and we will have one sent to every single former Emmy Noether lecturer as well, and give one to everyone in the future. So, congratulations.
So in fact, I hope that a picture of this plaquette will be put on the IMU website, where you can appreciate all the details. At the last meeting of the Executive Committee of the International Mathematical Union, we met the artist and we could comment. And the figure of Emmy Noether, she just looks alive, and you have the impression that she is going to talk mathematics to you.
And actually, the original design is much larger, and a copy of that design is one of the objects you can win with Don Auction. Don't forget to go to donauction.org.
So, Georgia Benkart is a leader in the representation theory of Lie algebras and Kac-Moody algebras, with fundamental contributions to several branches of Lie theory. Georgia Benkart's impact and influence have been fundamental to the growth of many careers of young people, with more than 20 PhD students. She had contributed profusely to mathematics through her services as office bearer at the American Mathematical Society, as well as at the Association for Women in Mathematics. Georgia Benkart was Paul Yale Lecturer of the Mathematical Association of America for 2000-2002, and a coincidence, she was the 2014 Emmy Noether Lecturer. This one is the ICM Emmy Noether Lecturer of the Association for Women in Mathematics last January. So let's now her speak to us in the same way as Emmy Noether was speaking to her students. Georgia.
Thank you. I would like to express my gratitude to the International Mathematical Union for the invitation. I'm deeply honored by this to give this lecture, named for Emmy Noether, who is somebody I greatly admire. Emmy Noether gave 2 ICM talks. The first one was a sectional talk in 1928, and the second was a plenary lecture. In fact, she was the first woman to give a plenary lecture at the ICM in 1932. This is a copy of the paper she gave at the ICM. The title was Hypercomplex Systems in Their Connections to Commutative Algebra and Number Theory. Or what we'd say now is algebras over the reals in their connections to commutative algebra and number theory. Biographers of Emmy Noether always comment that this was really the high point of her career. They also remark that she was very fond of walking. In fact, she developed many of her ideas in discussions on her walks with students and colleagues. Often she'd forget about the traffic. But fortunately, the traffic did not forget about Emmy Noether, and even more fortunately, the mathematical community did not forget about Emmy Noether. So I thought it would be appropriate to start with a walking problem. So let's just suppose we have a graph. The graph has 7 vertices. There's a roundabout on the outside. There's an island in the middle. And there are 3 two-way streets into the center of this island. We could ask very simple questions. How many walks are there from 0 to 0 of 8 steps? How many walks are there from 0 to 6 of 8 steps, or really any number of steps? And one way to look at this question would be to use something called the Bertelli diagram. This is a very common technique coming out of the study of operator algebras and subfactors and von Neumann algebras, and it's named for somebody from that field. So here's the idea. We'll form an infinite diagram, I only drew part of it, where at level 2, for example, I put the 2 places, the 2 vertices I could reach in 2 steps. So I can only reach 2 and 6. And underneath, I'll record how many walks are there to those 2 vertices. Then the next step, I'll just look at what I can reach from there, which is 3, 1, and 5, and I'll just add numbers like you do in Pascal's triangle. So when I get down to the very bottom, after 8 steps, I look at these numbers, 22, 64, 21, 21, and they tell me how many walks are there from the top to the bottom to these vertices in 8 steps. So the answer to the first question is 21. The answer to the second question is 64. Now, another very common technique here is to look at the adjacency matrix of the graph. So what am I doing here? Well, for example, if I look at the row number labeled by 1, I'll put a 1 in the places that I could reach from vertex 1. I can reach vertex 2, and I can reach vertex 6. So those columns I have a 1 in, and everything else I have a 0 in. And if I were to take the 8th power of this adjacency matrix, and I look at the row labeled by 0, then what that row is telling me, what those blue numbers are telling me, is how many walks are there from 0 to those vertices. So, for example, there are 21 walks to 4 to 0, and there's 64 walks to the vertex 6. So this is the same information that I'm getting from the Bertelli diagram. Now, if our graph has some other structure, for example, if it came from looking at groups and representations of groups, then I can say a lot more. So I'm going to talk about the following situation. Suppose I have a group, and suppose I have a finite dimensional G module over the complex numbers. What that is just a finite dimensional complex vector space on which the elements of the group act as invertible transformations on the space. And I'm going to form a graph from this group and this module. And the vertices of the graph are the irreducible G modules. These are the ones that I can't split up into a direct sum of two smaller modules. And the edges are exactly what happens when I take the tensor product of one of the irreducibles with the module V. So that's a G module, and then I'll decompose it into irreducibles. And these A mu lambdas tell me how many edges I should draw from mu to lambda. Okay. So I want to look at the number of walks of K steps from the trivial G module to lambda on this graph. The trivial G module is a one-dimensional module. Every group has one. It's one where the identity, every element acts as the identity transformation on this module. And it turns out that that's exactly the multiplicity, or how many times G lambda occurs in G0 tensor V tensor K, or in V tensor K. Because every time I take a step on the graph, I'm tensoring. So if I take K steps, I'm tensoring by K copies of V. So here's an example. Suppose you just take 2 by 2 matrices of determinant 1 over the field of 3 elements. So that group has 7 irreducible modules. There's a trivial module and 6 others. And here is what would happen if I chose each of the V's that are not the trivial module. So you notice that the first graph is the graph we just saw a little bit ago. The graph with the roundabout and the walks into the center. The graph for tensoring with the thing that I numbered G5 is just the same graph as the graph with G1, except I've changed all the one direction streets. I've changed the direction of the roundabout. Okay. What that tells me is that those are dual modules. So 2 and 4 are dual modules. 3 and 6 are very interesting. And if I were to unravel 6, then I'd get something that many of you probably recognize. This is one of the Affine-Dinkin diagrams. Okay. So unraveling this module V, tensoring with V, I get this Affine-Dinkin diagram. So you might wonder, why do you want to look at these tensor powers of this module V for any group? And the answer is that quite often you use them in building models. So for example, if you look at the group SU3 and you look at its 3-dimensional module, its natural 3-dimensional module, that's been used to build a model of quarks in physics. And if you take the k-fold tensor product, that's just modeling what the particles composed of k quarks look like? So it's an interesting question to study these tensor powers. So I want to talk about invariants, but I don't want to start talking about invariants until I tell you a little bit about Emmy Noether's work on invariants. So this was a large part of her mathematical and other contributions. And people generally divide her work into eras or epochs, whatever word you want to use. The first epoch, or the first era, was really devoted to invariant theory. Her 1907 PhD thesis ended with 331 invariants. And the methods were very constructional and very computational. Well, Emmy was not very happy with her thesis. She called it Formelgestrüpp, which roughly translated is a jungle of formulas. So after this, she became very interested in looking at an abstract way to do invariant theory, and became influenced by such results as the Hilbert basis theorem and other results in abstract algebra. In 1915, she was invited to go to Göttingen at the invitation of Klein and Hilbert. Hermann Weyl, who became much later her colleague at Göttingen and her co-walker, said that to both Hilbert and Klein, Emmy was welcome as she was able to help them with her invariant theoretic knowledge. In 1918, Emmy Noether wrote a very influential paper. In fact, it's so influential, it's just known by IV. And in this paper, she had a theorem that's now called Noether's theorem, which is a very fundamental result in physics. It says that a physical system is invariant under a group of symmetries if and only if some quantity is conserved. So, for example, if you have a physical system and you happen to see that it's invariant under rotations, then there's some kind of physical quantity conserved. Energy conservation follows from invariance under the group of time translations. So this result was quite influential because at the time Hilbert and Klein were very interested in general relativity, and so this fit into the kinds of things that they were looking at and studying. So Einstein, in a letter to David Hilbert, said, "Yesterday I received a letter from Miss Noether, a very interesting paper on invariant forms. I am impressed that one can comprehend these matters from so general a viewpoint." And it is an amazingly general result that just is very simple to state. The last about 15 years of Emmy Noether's life were devoted to abstract algebra and developing ideal theory. So now, I want to connect these two threads of Emmy Noether's life, walking and invariance. So let's take our finite group and let's take a finite dimensional G module and let's look at the representation graph. So as before, I'm using MK upper 0 to be the multiplicity of the trivial module in the k-fold tensor product. That's actually the dimension of the G invariance in the k-fold tensor product. Because each time you have a copy of the trivial module, you have one dimension of an invariant. So the number of the copies of G0 tells you how many invariants you have. the dimension of the space of invariants. But that's also the number of walks of k steps on the representation graph from 0 to 0. So I'm going to try to compute those numbers. And what I'd like to do is form the Poincare series, so this will compute them all at once, or give me a way of computing them all at once. So I'm forming this series, the generating functions for the invariants. And in fact, this sort of surprised me that it's really very easy to compute. It's just the quotient of two determinants. And in fact, I can factor the bottom. So let me explain what these determinants are. A here is the adjacency matrix of the graph. A0 is the adjacency matrix where you cut out the trivial module, you cut out the node 0. So you just compute these two determinants and then you know the generating function for all the invariants. This factorization into linear factors, I divide my group up into conjugacy classes, and I look at the character value of a representative of those conjugacy classes. That's just taking the trace of that element and its action on V. So this gives me the invariants. So it's also true that if I want to know how many walks there are from 0 to any point lambda, I do the same thing. I take the quotient of two determinants, and the bottom, the denominator, is the same for all these computations. So here's our favorite example. I hope it's become your favorite example now. You've seen it 3 times. So the first determinant, the one on top, is the determinant of this graph that I have over here on the right, where I cut out the point, the vertex 0, and just look at the graph that's left, and look at its adjacency matrix. The determinant on the bottom is I put that back and look at the adjacency matrix. And so when I compute this quotient, one determinant divided by another, then I get this infinite series. And what is that infinite series telling me? Well, it's telling me the subscripts on the blue vertices. So you look and you see, well, at k equal 4, that's the first time I see a blue vertex, a trivial module, after I start walking on the graph. And there's only one of those, and that corresponds to the coefficient 1 in the series below. The next time I see a blue vertex is when I look at k equals 6, and the coefficient is 6. And then there's our favorite 21 down at the bottom. Okay? So I could just keep dividing, assuming I don't make any mistakes, and figure out any sort of dimension of the invariants that I'd like. Okay, well, this gives me the dimension of the invariants, but how would I go about trying to construct them? And this brings me to what's called the centralizer algebra here. This is the set of transformations that commute with the action of the group on this tensor product space. It's something called the centralizer algebra. And why is that playing a role here? Well, it's playing a role here because it contains the projection maps onto the irreducible G summons. So if I want to find the G invariants inside that tensor product, I need to be able to project down onto them. And this is where I would look for that transformation. So this is going to play an important role. So Schur-Weyl duality is one of the most prolific concepts in this area of group representation. And what it does is it relates the decomposition of this k-fold tensor product relative to G to the decomposition relative to this centralizer algebra. So if I look at the decomposition relative to G, I know that those numbers that are coming up are the number of walks of k steps from 0 to lambda. But I can also decompose V tensor K into modules that are simple modules, irreducible modules, for the centralizer algebra. And what Schur-Weyl duality tells me, well, the first thing it tells me is that these two are in bijection. The labels are in bijection. The irreducibles for the group and the irreducibles for the centralizer are in bijection. And the second thing it tells me is that these green and purple numbers are related. And how they're related is that this d lambda is actually the dimension of the G module. And the green one, the mk lambda, is actually the dimension of the irreducible module for the centralizer. The next part of the Schur-Weyl duality says that if you want to know the dimension of the centralizer algebra, well, classical Wedderburn theory says you just square the dimensions of the irreducible modules and add them up. But that's adding up the squares of the dimensions of the number of walks that we have from 0 to lambda, the squares of those. And it's also the number of walks of 2k steps from 0 to 0 on the representation graph, because if I square the number, I go out to lambda, and then what? I reverse the path and come back some way. So that's why it's a square. So here's an example. Let's look at SU2. So this is a very well-studied group. Many of you probably have encountered it doing mathematical physics, maybe. It's the group of weak interactions in physics. So it's the 2x2 matrices where you have x and its conjugate on the diagonal and y and its conjugate, negative of its conjugate on the off diagonal, and it has determinant 1. The finite dimensional irreducible modules for this group, well, it turns out there are infinitely many of them. They're indexed by the non-negative integers. And the natural module is just this column of 2x1 matrices where I just act by a matrix by multiplying. And the Clebsch-Gordon formula says that when you tensor with this V, what happens is you get what you do by subtracting 1 and adding 1. Now, Paul Gordon had exactly one PhD student who was Emmy Noether. So walking on this representation graph is exactly just walking on the non-negative integers. You either move to the left, subtract 1, move to the right, or add 1. Here's the Bertelli diagram. So the numbers, for example, if you look at the row k equal 5, those numbers tell me that there are 5 paths from 0 to 1 of 5 steps. There are 4 paths from 0 to 3 of 5 steps. If I square those numbers, I get the dimension of the centralizer algebra, which is 42. But you notice those numbers, 1, 1, 2, 5, 14, 42. Maybe some of you have seen the numbers before. Well, everybody's seen the numbers, but seen the series before. Okay. So these are Catalan numbers. And the centralizer algebra then has dimension equal to the Catalan number. And what we know from Schur-Weyl duality is that the number of walks on the non-negative integers of length 2k that begin and end at 0 is given by the Catalan number. That's one of the hundreds of things that Catalan numbers count. And this is just one different proof of that fact. Okay. So this algebra, this centralizer algebra of SU2 is a very interesting algebra. It's called the Temperley-Lieb algebra. I'm going to try to describe it just briefly. This map E is given by taking a tensor and subtracting the tensor in the opposite way. This is projecting the two-fold tensor product of V, the two-dimensional module, tensored with itself 2 times, onto the trivial module. So the image is the invariance. Okay? But people have assigned to this a nice diagrammatics. The generators for this algebra, well, I'm just going to put that E into slots I and I plus 1 in the tensor product and apply it there. So I'm projecting slots I and I plus 1 onto the invariants. Here are the relations for the Temperley-Lieb algebra. And they should look like, sort of like braid relations. And in fact, this algebra is a homomorphic image of the group algebra of the braid group. So here's a typical basis element. It looks like this. I have k vertices on top, k vertices on the bottom. I connect each vertex to another vertex, but they're not allowed to, edges are not allowed to cross. And the way they multiply is you just stack them on top of each other and you concatenate the 2 diagrams. So you can follow what the answer would be. You can see how I followed the paths from the bottom to the top. There's going to be a loop in the middle, which you can see over here towards the right. And we're going to count each of the central loops and have a factor of 2 for each one of those. And that's coming from the first relation, TL1. So the Temperley-Lieb algebra has appeared lots of different places. So here 2 is x. You can replace the 2 in the definition by generators and relation by x. It first came up in statistical mechanics, where it was used to describe transfer matrices on a lattice and energy transfer. It's played a very important role in subfactors of von Neumann algebras in the work of von Jones. It's appeared in knot theory. So I just said that it's connected to the braid group. There's a Q version of that called the Hecke algebra. And if I look at the homomorphic image of this algebra with x equal q plus q inverse and take the image, which is the Temperley-Lieb algebra, then I can look at it, how it acts on various spaces and take the trace, and I get the invariant of knots and links. And this is how the Jones polynomial came up. It's connected to categorification. There's several talks at this ICM on categorification. You probably weren't watching, but I took a group and a module, and I replaced it with a whole category of algebras, these centralizer algebras, and their modules. So that's kind of what's going on with this categorification. I use that collection of algebras to study various representation questions, and it's also been involved in quantum computing. So now I want to sort of switch gears and look at the finite subgroups of SU2. And go back 130 years to a paper by Felix Klein, who showed by studying Riemann surfaces that the finite subgroups of SU2 are either cyclic groups, binary dihedral groups, or a binary tetrahedral group, which is also the group SL2 over a field of 3 elements. So that's where that example was coming from. Binary octahedral group, or the binary icosahedral group. And binary here just refers to the fact that it's a twofold cover of some very familiar groups. So if you factor out the center, which just consists of plus or minus the identity matrix, you get one of these groups, either the dihedral group of order 2n, an alternating group of even permutations on 4 letters, symmetric group of S4, or an alternating group A5. Very familiar groups. So in the early 1980s, there was a lot of work on singularity theory, studying singularities. And John McKay did a lot of computer experimentation. And one of the things he showed or observed was that if you take a finite subgroup of SU2 and you take its natural action on 2-dimensional space, just by matrix multiplication, the representation graph that we've seen all along is one of the affine Dinkin diagrams. They exactly match. Type A is for the cyclic groups, type D for the dihedral group, and E6, E7, E8 for tetrahedral, octahedral, icosahedral. But there's even more to the story. If you take the adjacency matrix, that's 2i times minus the Cartan matrix, the affine Cartan matrix. Well, the affine Cartan matrix is the prescription. It's all the information I need to construct a very important Lie algebra from this matrix, this information. That's the adjacency matrix of this representation graph, which is an affine Dinkin diagram. Dinkin diagrams, these affine Dinkin diagrams come with marks, numbers on top of them. And they have significance in Lie theory. But it turns out that those marks from Lie theory are exactly the dimensions of the irreducible modules for the group. Amazing. The eigenvectors for the Cartan matrix exactly form the columns of the character table of the group. And there are other things that just come up that seem like sort of miracles, this correspondence. So here's the correspondence. Here are the groups and their affine Dinkin diagrams. I've shown the marks. These are the dimensions of the irreducible modules for the groups. You notice they're not too big. Okay. So now I'd like to connect walking, invariants, and the McKay correspondence. Okay, so let's take a finite subgroup of SU2, and let's take its natural 2-dimensional module. Let's look at the multiplicity of G0 in V tensor K. That's the dimension of the invariants. That's the number of walks of K steps on the affine Dinkin diagram from 0 to 0. If we form the Poincare series of those G invariants, well, we already know that it should have this form, because that happens in every case for any finite group in any finite dimensional module. But in fact, we can factor both the top and the bottom and say more about what these linear factors are. So let me just put down what all these things are, and then I'll explain them. So as before, A is the adjacency matrix. This time, since the representation graph is the affine Dinkin diagram, that's the representation, that's the adjacency matrix of the affine Dinkin diagram. A0 is the corresponding finite Dinkin diagram. And I'm just taking the determinants of basically those two matrices here. Gamma, as before, is the set of conjugacy class representatives, and chi gamma is the characters. Okay. H is the Coxeter number for A0, or H hat is for A. If I look at the Coxeter number for the finite Cartan matrix, the finite one, I get it by adding up the marks on the affine Dinkin diagrams. So I get it by adding up the dimensions of the irreducible modules for the group. Okay. What are these E's? Well, these E's are the exponents. They're the exponents of the Weyl group. So every Dinkin diagram has connected to it a group of reflections called the Weyl group. There are certain numbers connected to that Weyl group called the exponents. If I take the exponents and add 1 to them, what I get is the degrees of the generators of the polynomial invariants of the Weyl group. So the Weyl group acts on a certain polynomial. The number of variables of that polynomial is exactly the size of the Cartan matrix. So what this result is doing is it's connecting the invariants, the tensor invariants of the group G, to the polynomial invariants of the Weyl group. Okay? Okay. So in fact, you can see also that it's connecting these cosines, which come up by adding together just primitive h roots of unity, or h hat roots of unity, adding 2 complementary ones. It relates those to the character values of the group G. So we're relating tensor and polynomial variants of these different groups. Okay, here's what I'm, sort of an example of what I'm saying here is that if I look at these determinants, well, the top determinant is just the adjacency matrix of the Dinkin diagram of type E7 for the octahedral case. For the denominator, it's put back that blue node. And you just compute, divide, as long as you compute 7 by 7 and 8 by 8 determinants, you can compute the degrees of the invariants, dimensions of the invariants. And those are the numbers that run down the right-hand or left-hand column. Okay, so in joint work with Jeff Barnes and Tom Halverson, we connected Schur-Weyl duality and the McKay correspondence. So tried to bring together these two very important ideas. So I'll explain what's going on in the cyclic case. So let's look at the cyclic group as it sits inside of SU2. So I have a primitive nth root of unity on the diagonal. The irreducible modules for the cyclic group, well, the cyclic group is an abelian group, so the irreducible modules are all going to be one-dimensional, and they're given by the various powers of this primitive nth root of unity. Tensoring behaves where you just add the superscripts. mod n. So this is kind of gives a mod n Clebsch-Gordon formula. Okay. So what does the Bernoulli diagram look like? Well, you start at 0 and you subtract 1 or add 1 mod n. So this is the Bernoulli diagram for the cyclic group of order 5. I subtract 1 and I get minus 1 mod 5, which is 4, or I add 1 and I get 1 mod 5. And I keep going down like this. When I get to level k equal 4 and I do the next step, I add 1 and I have to run around to the left-hand side. Okay, so what is this? This is just Pascal's triangle on a cylinder of diameter 5. What happens if I switch to the cyclic group of order 10? Well, I really did switch the slide. It's the same Bernoulli diagram, it's just the labels are different because only half of them show up at each level. So again, I get a Pascal's triangle of a cylinder of diameter 5. So I'm going to have to do a little bit with parity here. So if I set n tilde equal to n if n is odd and half n if n is even, and I look at the tensor power and I take a basis, well, I could label the basis with zeros and ones and think of them as bits. Here it's more convenient to label them as minus ones and ones and work with them there. And then I look at a k-fold tensor and I just sort of count up how many minus signs I have. And the way this generator of this cyclic group acts is it just gives me a power of zeta, and the power is k minus 2 times this value of r. So when are those two of those equal? Well, they're equal mod n, because this is a primitive nth root of unity. They're equal mod n if and only if the number of minus signs in each are equivalent mod n tilde. So that's where the parity is coming up in the calculation. So a basis for the centralizer is just matrix units. These are just the transformation that preserve this eigenspace, right? Anything that commutes with the transformation that's giving me the eigenspace is going to be in the centralizer. So let's count them. So I need to count how many k tuples do I have such the number of minus signs are the same, mod n tilde. And if n is very large, they have to be the same. So that tells me, I'm writing C infinity, but I just mean n is bigger than k, so the parity doesn't come in. So the number of these matrix units, which is the dimension of the centralizer algebra, is, well, I am counting the ones that have the same number of minus signs. Let's call that A. So I have k choose A places for the top ones and k choose A for the bottom ones for where to put the minus signs. And everybody know what this is? Okay. Agreed? Okay. So this is the coefficient of zk in 1 plus z to the k, twice. So in other words, it's 2k choose k. Everybody knew that, right? Okay. So now the only modification I have to do for the case that I'm really interested in is that I just have to make sure that I'm taking k choose A, k choose B, and A and B are congruent mod n tilde. And that's the coefficient of zk in 1 plus z to the 2k modulo z to the n tilde is equal to 1. That's the number of walks of 2k steps from 0 to 0 on a circular graph of n vertices. So here's a quick example. You just take k equal 5. I look at 1 plus z to the 10th. I expand that out like I did at some point in 7th grade or 6th grade. And then I look at the powers of z mod 3, because n is 3 here. And then all I have to do is combine those and get the dimension. So that's how I compute the number of walks of 2k steps from 0 to 0 on a circular graph. If I take the irreducible module for this centralizer algebra, well, it's very similar. I just take the minimum number of minus signs that I can solve this congruence for, and the dimension of the irreducible module is just the binomial coefficients k choose b, where b is congruent to a mod n tilde. That's the coefficient of za in 1 plus z to the k modulo z to the n tilde equal 1. That's the number of walks of k steps from 0 to lambda on a circular graph of n vertices. So here's a quote. A fair number of real-world problems lead to random walks on groups. Think of the integers mod n as n integers wrapped around a circular graph. The simplest random walk is a particle that moves left or right, with probability a half. How many steps does it take for the particle to reach a given site? How many steps does it take to the particle to hit every step? After how many steps is the distribution of the particle close to random? So I haven't talked about probability, but these are the same types of questions that I was answering by looking at these centralizer algebras. And you can probably guess who said this. Okay, this is Percy Diaconis. Okay, so I want to just talk briefly about the structure of these centralizer algebras. I have a finite group living inside of SU2, so what commutes with SU2 is going to commute with the finite group. And that means that all of them contain the Temperley-Lieb algebra. So I have these generators of the Temperley-Lieb algebra, and the question is, what else is in there? What else? What other kind of generators? And what we used to study this question was actually results from Von Jones's work and Hans Wenzel's work on towers of algebras, things that came up in looking at von Neumann algebras, and the idea that the centralizer algebras form actually a tower of algebras. They embed one in the other. And inside the tower of algebra is a very big ideal, a very big of two-sided ideal sitting inside of one of these centralizer algebras. And this big ideal tells me that it has the same irreducible modules as 2 steps above. So we're just moving down this tower of algebras, and we're looking at the irreducibles. They're in bijection. And there's a very beautiful reflection property that comes up that says the restriction from this big ideal to the algebra 1 step above is the same as induction from zk minus 1 to zk. So in this picture, the irreducibles for zk minus 1 and zk plus 1, ek, zk plus 1, are these 2 things numbered by 0 and 2. And the reflection property is saying gray reflects to pink. Okay? So if I were to restrict the irreducible module labeled by 2 to level k, it would break up into a sum of 1 copy of 1 and 1 copy of 3. Gray reflects to pink. So what this tells me is that if I look at the Bernoulli diagram, and I look at the edges that reflect, so the edges that are black are the ones that reflect from other edges. They come from this Jones basic construction. They come from building up from below. And the ones that don't come from that are exactly right on the money, the representation graph. Amazing. Here's the binary octahedral group, and you can see that the edges that don't come from reflection are exactly the blue ones, which is the representation graph. Notice also that as we move down the right side, looking at the numbers, we see 1, 1, 2, 5. Oh, I'm getting Catalan numbers. But then I hit the bump in the road, the branch. And at that branch, I have to add one more generator. So every time I hit a branch, I add a generator. And after that, I don't have to add generators in this particular one because I only have one branch. Well, the McKay correspondence is connected to so many things. It's connected to mirror symmetry. I know I'm supposed to apologize when I say the word cohomology of moduli of Calabi-Yau manifolds, connected to singularities. Here, I just want to very, very briefly connect it to partitions. So this is kind of a new connection for the McKay correspondence. So we know that the center of the group acts trivially on the twofold tensor product. So there's an action of the group mod at center on the twofold tensor product, and these are very nice, familiar groups. Symmetric group on 4 letters, alternating group on 4 or 5 letters. And it turns out for A4 and S4, this V tensor 2 is a twist of the permutation module. So that's just the module where the basis is indexed by 1 up to 4, and the group permutes those. So this tells me that the centralizer algebras in these cases are really the centralizers of these symmetric groups or alternating groups coming from looking at partition algebras, permutation algebras. And that centralizer is known to be the partition algebra, quotients of partition algebra. So the partition algebras were introduced by Paul Martin to study interacting spins on a lattice in statistical mechanics. And they're just sort of glorified Temperley-Lieb algebras. They have a basis consisting of 2 rows of L vertices each, and you just connect however you like, just so long as you don't end up with more than 4 blocks if you're working with a symmetric group S4. Okay. So it's sort of like Facebook, right? You don't care how you're connected. You just want to know who am I connected to. And that's the only thing that's important here. It doesn't matter how you draw the diagram. It's just who are you connected to. And using results on partition algebras from Paul Martin and Von Jones, who established a Schur-Weyl duality between partition algebras and the symmetric group, we know that the irreducible modules for these partition algebras are labeled by partitions of the number 4. Okay, so partitions are used here twice. Amazing. And so I get this for my Bernoulli diagram in the partition language. So you notice, for example, at level 3, you see the partitions of 4. 4, 3, 1, 2, 2, 2, 1, 1, 1, 1, 1, 1. Wait a minute, where did those partitions of 3 come in? Okay. So the partitions of 3 came in because people had the insight to put them there. In other words, the people who were 15 years ago, Paul Martin, Ricolet, said that the way to really study partition algebras is to do the following, to restrict from S4 to S3, and then to induce back up. And one thing this does is it allows you to avoid having multiple edges. Okay. So this says that I can take my representation graph now and decorate it with partitions. Half the nodes are decorated with partitions of 4. And the amazing result is those marks that we saw before are exactly the dimensions of the irreducible modules for S4. The marks of the ones that are labeled in 4 are twice the dimensions of the irreducible modules for S3. But remember, we've got to put the center back when we look at the odd tensor powers. So you can think of walking on the Dinkin diagram as, oh, you have to throw away a box, being careful not to litter, if you're going from 4 to 3, or you have to add a box. Okay. Same thing happens for the alternating case. You look at L equals 2, you get all the labels for the irreducible modules for the alternating group A4. Again, we can decorate the Dinkin diagram with partitions, the partition labels for the alternating groups. And again, the dimensions work out exactly perfectly. So somehow the McKay correspondence has kind of a refinement that you can refine to these partitions of 4, partitions of 3. Okay, so what happens in the icosahedral case? Well, icosahedral case, V tensor 2 is not the permutation module. It's not a twist of it. It's a sum of a 1 and a 3-dimensional module. Okay. So this means that you're in trouble, that you have entirely different techniques that have to be used. The dimension of the centralizer algebra, in fact, involves something called the Lucas number. The Lucas number is a Fibonacci number that got off to a bad start. So it satisfies the same recurrence relation. The only difference is the starting point is 1 and 3, which just happen to be the dimensions of the irreducible modules that this decomposes into. And it's related to the golden ratio. Okay, so I don't have time to talk about this. More walking is needed. I'd like to give my thanks to Emmy Noether for her inspiration. Kamsahamnida. Thank you.
Well, thank you, Georgia, for a very inspiring talk. And it's a great closure of this day and also of the ICWM. So it was the International Congress for Women in Mathematics. I used the opportunity to thank again the organizers of this Congress, in particular, Aug14Thu. And thank you again for the lecture.